and combustion. His focus of study is micro hydropower plant and education for renewable energy. And he's also the Vice Dean of Corporate Affairs, Business and Information of Vocational School of Universitas 11 Maret. So ladies and gentlemen, I present to you our dear moderator, Dr. Herman Saputro. The time is yours.
Okay, thank you, Mr. Albert, for master ceremony today. So thank you very much for all participants. First, Honorable, our speaker, Professor Wei Cheng Wang. I usually call Professor Wang from Center Research for Information Technology and Innovation, National Cheng Kung University, NCKU Taiwan. It's also my colleagues from Taiwan. And good afternoon, Professor Wang.
Yeah, good afternoon. How are you, Professor Saputro?
Okay, so distinguished participant, International Conference on Smart Technology, Applied Informatics and Engineering, APICS 2022. So now we're going to the interesting plenary section. Today we have Professor Wang, and Professor Wang, let me introduce Professor Wang. Professor Wang graduated from North Carolina State University, USA, and field specialization, process and system design from renewable fuel production, and then the master degree from Lahig University, Bethlehem, USA, and bachelor degree from Fengsha University, Taichung, Taiwan. And then Professor Wang, the research interest in energy conversion and system integration, experimental fluid dynamic, process evaluation, and renewable fuel and combustion, wind power and system design. So many interest research from Professor Wang. And then Professor Wang also the expertise related to UN Sustainable Development Goal. So Professor Wang also interested in the SDGs research. So I think it's very complete today. So we have a good plenary session from our speaker today, Professor Wang. And then today, Professor Wang, he would like to present about the net zero for aviation. I think this is the good theme and good topic today. Hopefully, all the participants can study more deeply from Professor Wang. So, please, Professor Wang, the time is yours to present your material related to net zero for aviation. Please, Professor Wang, this time is yours.
Okay, thank you, Professor Saputro, for the introduction. And thank you for the invitation. I'm glad to talk to you and discuss with you about the new idea. If I'm changing a slide and the slide is not showing, it's not updating, please let me know. Yeah, I can do some change. Okay.
Okay.
Is the slide showing okay?
Yes, Professor Wang.
Okay. So today my topic is quite a very fancy topic for you. We call net zero. So net zero is now very important. Net zero is now very important for everywhere, for industry, for school, for the community, okay, for government. They want to reduce their carbon as much as they can, okay? And as I stay in, let me introduce myself first. Okay, I have my education in mechanical and aerospace engineering, North Carolina State University, and my current position actually is something I want to correct. I'm from Department of Aeronautics and Astronautics, National Cheng Kung University, NCKU. And previously, I worked in National Renewable Energy Lab. It belongs to U.S. Department of Energy. And that's where I graduated from, Lehigh University. I got my master's degree. And so far, my research interest is the liquid fuel production and the combustion test for these kind of fuels and thermal conversion system development. Is the slide changing okay?
Okay.
Yeah.
It's already changed.
This is my lab, the fuel and combustion laboratory. And we work on novel fuels, okay, new fuels, especially low carbon fuels. And for fuel, and once we produce the fuel, we do the fuel combustion and pollution analysis. Also, so far we got a few projects related to the waste to energy thermal process development. I think this part, Professor Sapocho has a great experience on that. And so far we work together on this. And I got 2 PhD students. One of them is from your university. And I got 8 master students and 6 international students. And these are the journals we have been publishing our papers, share our research. So we have a little bit international collaborations. Here is Professor Sapocho, Herman Sapocho from UNS and for Indonesia. And we also work with Malaysian Professor Wen Tong Jong from UM. Yeah, and also the Vietnam professors, Korean professors, and Thailand professors, Denmark professors, okay, Australia professors as well, and New Zealand professor, okay. And these are, let's say the overall research what I've been doing. So the left-hand side, you can see this side is the fuel, let's say the fuel, or we call waste to energy. So we make fuels, the new fuels, clean fuels, low carbon emission fuels. And we also do the combustion test. For example, here we do we use the constant volume combustion chamber as well as the rapid compression machine to test the ignition. I will discuss in the following pages. And also we do the laser diagnostics for looking at the flame behavior, for example, the laminar flame speed and soot formation in the counterflow burner. And later on, we will be testing that in our constant volume combustion chamber. Also, we use the pyrolysis, vacuum pyrolysis, as well as the gasification, plasma-assisted gasification to produce the hydrogen. So we produce the hydrogen from the waste, okay? And we use the hydrogen energy to produce the electricity. So that's our waste to energy process. Meanwhile, there's a CO2 capture to assist the whole processes, okay? And so far, we are trying to look at if our absorbent can capture the CO, but now the CO2 capture works very well, okay? So these are all our researches. So starting from our topic is net zero for aviation, which means you want to fly for net zero. So this is a quite interesting topic because for aviation sector, no one cares about the carbon emission because it's on the sky. Okay? I mean, everything on the sky is not our business. So for on the ground, transportation on the ground like trucks, cars, okay, industrial boilers, okay, we look at very seriously the carbon emission, but the sky, the aircraft on the sky, nobody cares. So that's why there should be someone taking care of, taking care of the carbon emissions for the aircraft. Okay, so this is why I choose this topic. We call it a fly net zero. Okay, so for the fly net zero, the first thing we are trying to do is, okay, because there's someone they propose electrical flight, but well, for small aircraft, for UAV, it's okay. But for big aircraft, what I'm saying is I need more propulsion. I need more lift. The aircraft is like tons, like very heavy. You cannot use the electrical. Somebody proposed the hydrogen, okay, but it's not the technology is not very mature now. So the thing we need is we call drop-in. We need a drop-in fuel. We need a drop-in fuel first, to overcome the technology, and it will fit. We call fit in purpose, like we can fit in our jet engines. Okay, so that's bring our target is okay. Then maybe we look at a clean aviation fuel, which means how clean is that? Yeah, the quality, the property, the combustion characteristics will be exactly the same as the jet fuel, normal traditional petroleum jet fuel, but eventually the emission, when it comes out, after combustion, when it comes out, the emission will be low, the pollution will be low, the carbon emission will be low. Okay, this is our target. So for doing this, we need to do many steps. Okay, I'm listing out these steps. For any of the products, we always start from the lab. Okay, this is the job for we professors. Like, okay, we work very hard in the lab, for probably stay in the lab day and night, day by day, and eventually, okay, we produce something after 10 years, 20 years. Okay, eventually we produce something, and we need to test it. So we test through the combustion test. And then we need to know the market. Okay, you produce something, you need to sell it. Otherwise, your product is just, let's say, garbage. Okay, so if you cannot sell your product is nothing. So you need to you need to evaluate your process. And nowadays, not only economics, but also people are looking at their energy, their environment. So they call 3E, energy, environment, and economics. They call process evaluation. And then we look at the source. So we need to find a good feedstock. We're looking at a source. And then once we have a tons of fuels, we need to test it. So we do the transportation test. We can test in a commercial flight. We test in military flight. Okay, and then we commercialize it. Then we look at how to distribute. Okay, how to distribute. For example, for liquid fuel, the distribution is okay, but for gas fuel, the distribution is a problem. So this is also a big deal, and distribution is including the storage. You need to think about, okay, how am I, if I have a tons of fuel, how to if I store it, it's the safety is okay, it's the storage is okay, is that going to be downgrade? Okay, so distribution is including the storage and then for daily use. So these are the long process. It takes like 20 years, 30 years, even 40 years. Okay, the famous example is biodiesel. Biodiesel, starting from the lab, it takes like perhaps 50 years to be commercialized. Okay, so starting from the first laboratory development. Okay, once again, go back to our process. For today's presentation, what I'm going to present is the first 3 steps, because I only do the first 3 steps. I cannot, no one can do it all, okay? No one can do it all. So I only do the first 3 steps. And I will start from the first one, and then second one, and third one. Okay, let me start from the first one, which is the laboratory development. For laboratory development, what I want to discuss is, number 1 is, how am I going to produce the fuel, the clean aviation fuel, the new novel jet fuel, and how am I how am I find out the property of the fuel I produced, and from the various feedstocks, okay, various sources. So let's look at the component of the fuel. So the gasoline you've been using, okay, it contains this kind of components, okay. For diesel fuel, it contains this kind of components. But for jet fuel, it has 2 types of jet fuel. If you look at the Jet A1, the Jet A1 is for commercial airplane, like this. But you also have to look at JP5, because JP5, or sometimes they use JP4, there's a JP8. Jet propulsion 5 is for military aircraft. So for these 2 types of fuels, they have, most likely, they have these components. What I'm saying is alkanes, isoalkanes, alkenes, acetylene, cycloalkane, and aromatics. Okay. So for jet fuels, okay, you can compare to diesel. So jet fuels, for the specification, we have to look at acidity. Okay, aromatics has to be 25%. Sulfur content, the maximum is 0.3. Final boiling point 300. The fresh point, especially, it has to be 38. It has to be 38. Fresh point is the temperature. The temperature when it reach, for example, 38 temperature, you will flush. Okay, and density and freezing point, it has to be -47, which means you have to go lower than -47 for maximum. Viscosity is 8, and heating value 42.8. Small point is 25, and CTN number is not available. Okay, because for jet fuels, I think previously no one considered their ignition so they don't really care about the ignition of the jet fuels. So for CTN numbers, normally they don't really look at their CTN numbers. Okay, so these are our targets. What we want to make is something similar to this. Okay, so to get our target, once again, we need the alkanes, isoalkanes, and aromatics. So aromatics, 25% is the maximum. But based on the new regulation for SPK, synthetic paraffin kerosene, the aromatics can be 8%, and cycloalkane has to be 25 to 30%. Okay, what's the feedstock? Okay, what's the hydrogen? And it goes through some processes. Okay, goes through some hydrogenation, hydrogenolysis, go through the deoxygenation. I remove my oxygen. Okay, and it produces the straight chain alkanes. And then go through some isomerization or aromatization or cracking. I can produce the alkanes, isoalkanes, and cycloalkanes. Okay, and after some distillation separations, I can make my jet fuel. I can make my jet fuel here. And this jet fuel, I give it a name because it's from hydrogen. So go start from H. It's renewable fuel. So R, and it's a jet fuel, so J. So I call it HRJ. Okay. So these are our processes. And so for doing this process, okay, once again, our carbon has to be Ca to C16, and the IN number, which means the iso alkanes to the normal alkanes has to be 1.5. So it has to be IN ratio has to be 1.5. The yield, the higher the better, of course, because you have more fuel produced, you have a lower cost. So yield has to be high. The aromatics has to be 8%. Okay, so for producing the fuel, we try different feedstocks. We try glyceride-based oil. What is glyceride-based oil? For example, the palm oil, vegetable oil, or wax cooking oil. They are called glyceride-based oil. Or we can try pyrolytic oil. What is pyrolytic oil? It's something, the oil produced from pyrolysis. Okay. We can choose different reactor. We can run different operating conditions, the temperature, pressure, hydrogen feedstock ratio, the WHSV, LHSV. What is that? It's a residence time. It's the flow rate by the volume. So it's a residence time, like per kilogram per volume of the catalyst bed or catalyst, what is going to be your flow rate, the feed flow rate. That's one of the conditions. And also we'll look at how long the catalyst will die, and for the regeneration as well, how to make it alive. Okay, and results, the important result is the conversion, how much fuel I can convert, and what is going to be the selectivity, and that will give me the yield. And what is my IN ratio? Is my IN ratio going to be 1.5, or is higher or lower? That's very important. And what is going to be my content of aromatics is also important. Okay, and also, by the way, the content of aromatics will affect the combustion characteristics. That I will discuss later on. So we look at the liquid fuel properties. Also look at the carbon distributions. We will also look at the catalyst performance and regeneration. So these are the GC diagrams we produced. So the first GC diagram is the HRJ, the hydro, what we call it HRJ, is the novel jet fuels we produced in our lab. So this HRJ, we can see from CH to 17. Okay, compared to JP5, I think I mentioned previously, it's the jet propulsion 5, which used in military fuel. And this is the commercial, the fuel used, JA1 is a commercial fuel used in commercial aircraft. So you can see we have, most likely, we have a little bit CH, and also we have some heavy products, but because the HRJ, the renewable fuels, is not coming from crude oil, so they would have some heavy products for sure. So we can always cut it off. Okay, I can cut it off right here or cut it off right here. Okay, I can make my HRJ similar to JP5 and JA1. Okay, I can also blend it. I can also blend my HRJ to JP5 to JA1, so it will fit. It will dissolve and it will fit. Okay, so we can distillate higher and heavier products and concentrate the product in the target carbon chain. Okay, so what is going to be the properties? The properties Okay, in terms of density, viscosity, heating value. So we compare our fuel. Once again, the H means hydrogen, hydroprocessed renewable jet to the Jet A1. We compare to the commercial aircraft fuel. So you can see the density is similar. Viscosity is a little bit low, but it should be acceptable because the maximum 8, which means lower than 8 is acceptable. Heating value, it's higher, which means it will give more energy. Our fuel will give more energy. Sulfur content less than 1, which is good for the environment. Total aromatics, we are 8, okay, and the maximum is 25, and 8 is already appropriate for the new regulation for SPK. Okay, C10 number is 55.9 compared to Jet A1 is 45.4, which means our fuel is more easy to be ignited. All right, which is good. And flash point is 64. Okay, compared to Jet A1 is 48, which means our fuel is safer for transportation or storage. It's safer. All right, and small point. Okay, small point is 62. So what is small point? The higher the small point, the lower the possibility that will emit the soot, or we call smoke. Okay, so compared to Jet A1, we have quite high small point, which means our possibility to produce soot, produce smoke is much lower than regular traditional jet fuel. Auto ignition temperature is similar. And the last one, which is quite an important one, is we call hydrogen to carbon ratio. Our hydrogen to carbon ratio is 2.15, and compared to jet fuel is 1.9. Okay, which means the fuel, the hydrogen content compared to the carbon content is higher. What does that mean? Which means we are going to have better combustion properties. Later on, I will discuss about this. So for the co-product, okay, for the co-product, there's a co-product produced was our HRJ, hydroprocessed renewable jet. We call renewable diesel, or called HRD, hydroprocessed renewable diesel. Okay, so we also compare this to the traditional diesel fuels. We can see, so that we compare to petrol diesel, we compare to biodiesel in terms of cold flow properties. Okay, which means the cloud point. You can see our cloud, the diesel fuel is -20, biodiesel is -5, and normal diesel is -12. So our HRD is better. Okay, in terms of heating value, in terms with the heating value right here. So heating value is also better. Okay, compared to biodiesel and diesel. C10 number is right here. Our C10 number is 77 compared to biodiesel 47 and normal diesel 53. Our diesel is better, which means it's easier to auto ignite. Okay, and there's no oxygen, good for storage, and similar spray characteristics as petrol diesel, no aromatics, so no real about soot formation. Okay, so these are the good thing for this co-product. And the better the co-product, the better the cost, the lower the cost. Okay, because if the co-product is good, then we can sell it. When we are producing it, we will have more buyers for our HRD, which means that will bring down our cost, right? So when we are trying to produce jet fuel, renewable jet fuel, okay, we start from, we call HDO. What is HDO? Is hold on. Okay. What is HDO? HDO is this. Okay, it's our when we deoxygenate it. Okay, remove the oxygen, we will have the straight chain alkanes, and this guy we called HDO. Okay, so we start from HDO, the straight chain alkanes. Okay, so and then we do different temperatures, we do different pressures, and we do different residence time, and we see the carbon distribution. And this is quite important. Why? Because later on, I will introduce our combustion studies. So once the combustion studies is telling us what kind of carbon range we want, and then we just tune our temperature, tune our pressure, and tune our residence time, and then we will get different carbon distribution. Okay, once we get different carbon distribution, then I will get better combustion characteristics. So that's how the fuel producer works with combustor designer. Okay, I can change my fuel quality property. I can change my fuel component, and then I get different combustion characteristics. Okay, so we look at different carbon distributions. All right, and for starting from straight chain alkanes, like I say, if we want to have, let's go back. So if we start from straight chain alkanes, we need to go through isomerization and cracking, because I need to make the carbon range located at A216. Also, I need to have more isomers to make I2N ratio 1.5. Okay, so I need to do isomerization and cracking. Okay, and isomerization is a slight exothermic reaction, so it will absorb emit the heat, and cracking need to absorb the heat. So they are different reactions. Okay, and cracking is more sensitive. So cracking is more sensitive to the temperature, which means you have higher temperature, you have more cracking for the reaction. Okay, and cracking start from the middle range carbon, so your product will concentrate on Ca to C9. Also, you have a higher pressure, you have higher cracking. That's how we found. You have the shorter residence time, you have lower cracking reactions. Okay, that's in terms of carbon distribution. And then what about ion ratio? I think everybody still remembers what I said about our I2N ratio. Okay, I2N ratio has to be better to be 1.5, no bigger than 2. Okay, so maybe at this range for temperature, residence time, and pressure, okay, this will be better. So let's say because high pressure will favors the isomerization. So we give higher pressure, the I2N ratio will be higher. Okay, what happened? Everybody might have a question. What happened if we have the higher I2N ratio? We have a higher I2N ratio, which means we have a higher isomers compared to normal alkanes. If we have higher isomers, which means we have a longer ignition delay. We have a higher ignition delay. Okay, you have a higher isomers based on our studies. You have a higher formation. So higher isomers is not good for our. Later on we'll discuss the detail, but it is not good for our combustion characteristics. So we try to make it 1.5. What about lower? Lower is bad. Lower is bad because we need to maintain the flash point. We need to maintain the flash point by 38. I think I mentioned before, I maintain the flash point by 38. So we gotta have some isomers in there to maintain the flash point. Okay. And aromatic content, okay. Sorry, Professor Sapoto, I probably need to charge it, my computer. Yeah, is that okay? I just
okay, no,
for
no.
1 minute or for 1 minute. I'm sorry.
Okay.
Okay. So back to our discussion. So as everybody remembers, we need 8%, that is 8% for the aromatics. And you can see if we have a higher pressure, the aromatics will decrease. If we have a higher temperature, the aromatics will increase. Okay, because the producing aromatics is the dehydrogenation, which favors at high temperature and low pressure. Okay, so if you have a high pressure, it will move to isomerization instead of making aromatics. And very important is why we need aromatics, because you need to, for the fuel tank, you need to have the seal. Okay, so aromatics, you need some aromatics to protect the seal. And also, we cannot have too much aromatics, because more aromatics, later on we'll introduce this, more aromatics, it will produce more soot, which make our fuel not clean, even become dirty. So we don't want to have more aromatics, okay? And we also try different feedstocks besides the glyceride-based oil. We try pyrolytic oil. Okay, so for pyrolytic oil, you can see we have, the pyrolytic oil comes from waste-derived pyrolysis. Okay, waste pyrolysis. So you can see the sulfur content is 0. Aromatics is 28. It's a little bit higher. So that's something we have to work on, like to reduce the aromatics. Okay, and vapor pressure is about 2.28. Molecular weight is similar to the normal jet fuel. Okay, hydrogen to carbon ratio, it's a little bit lower than normal jet fuel. This is not, like I say, you have the hydrogen content compared to the carbon content is lower, which is not that good. So that's something we have to improve. Density is similar, viscosity is similar, and heating value is a little bit lower. So for waste-derived pyrolytic oil, I can say this is not very, the jet fuel is not produced very successfully, but that's something we are working on, we can improve, okay? So the next part we're trying to work on is the fuel combustion test. So we do 2 types of fuel combustion study. One is the ignition delay, and one is the soot formation. So for ignition delay, we use the constant volume combustion chamber, and we try different pressure, we try different temperature, okay, we try different fuels, okay, and this is the constant volume combustion chamber in our lab. So we want to look at the cool flame ignition delay. So what is a cool flame ignition delay? This is our cool flame ignition delay. Okay, and it's a tau 1. Tau 1 is a first stage ignition delay. So tau 1 first ignition delay includes the cool flame ignition delay. And also we look at second stage ignition delay. Okay, and the first stage and second stage ignition delays, they combine our total ignition delays. Okay, we also want to look at how much energy released. So we look at the heat release rate, Okay, so we want to look at cool flame ignition delay, first stage and total ignition delay, and heat release rate. Also, there's a very important thing, is the negative temperature coefficient. So what is the negative temperature coefficient? So nowadays, for people doing combustion, they always want to do low temperature combustion. Why? Because low temperature combustion, you don't need to worry about NOx. All right. So this is the low temperature auto ignition mechanism. Okay. So for this mechanism, for people working on combustion, they should be able to know that, okay, you need to look at the chain initiation, starting from chain initiation, and then chain branching, and to the end is chain termination. Okay, so this includes the chain initiation, chain branching, and chain termination. Okay, but the most important two routes we are trying to look at is the number one is what we call edge abstraction, which means when you are doing the combustion, they're trying to grab the hydrogen atom, or trying to grab the hydrogen atom produced and combine with water to produce the maybe HO2 or something like that. So the ability of edge abstraction is very important. Another one is isomerization. Okay, so these two routes, these two mechanisms are very important for low temperature ignition mechanism. Okay, and in terms of low temperature combustion, you can see this plot, if this is the ignition delay to the temperature, and this is the low temperature region, intermediate temperature region, high temperature region. So normally in our imagination, it should be like the ignition delay, which means the lower ignition delay, the more active the fuel is. So when you increase your temperature, it should be the ignition delay should be decreased. However, during the intermediate range, the ignition delay will jump up a little bit. They'll jump up a little bit, which means it's kind of a very interesting part. Okay, the activity at intermediate stage will decrease, which means the ignition delay will increase a little bit. That's something people want to look at. Why is that, and what happens if I test different fuels? Okay. So this behavior comes from chain branching and radical propagation, especially for cycloalkanes. So for fuels with cycloalkanes, actually most of the fuel has cycloalkanes. For fuels with cycloalkanes, they all have the phenomena like this. Okay, so we try to look at the total ignition delay. This result we published in Fuel. The total ignition delay decreased was the increase in temperature, that's for sure. Okay, and also depends on, like I say, edge abstraction and isomerization. And the size of the carbon hydrogen bond influence the stability of the H atom abstraction, right? Especially if you have the higher hydrogen to carbon ratio, okay? Then go back to our previous discussion. We have the hydrogen to carbon ratio, all right? If you still remember the fuel we produce, which we call HRJ, the HRJ has the hydrogen to carbon ratio about 2.15, compared to the JA1 or JP5, it's 1 Okay, there's a difference. So you have a higher hydrogen to carbon ratio. So you have a better ability for H abstraction. Then you have a good low temperature ignition. So This is what we want to look at. See, at low temperature, this part is low temperature. Okay, you can see the new fuel we produced is much lower than JP5 and JA1 than the traditional jet fuel. Okay, this is the new fuel. This is the traditional fuel. So at low temperature, we have a lower ignition delay, which means our ignition is better. It's better, much better at low temperature. But going to the high temperature is similar. Going to the high temperature is similar. Okay, which means at low temperature, our fuel it's easier to be ignited. Okay. Also, you can compare the JA1, which is used in commercial flight, and JP5, which is used in military flight. JA1 is shorter than JP5. The ignition, in terms of ignition, JA1 is better than JP5. Okay. So that's the cool flame ignition delays. And why we started a cool flame ignition delay? Because cool flame ignition delay, you need more energy released to compete the vaporization, the heat vaporization. Okay, so we want to look at which one provides higher specific energy during the chain initiation process. Okay, then it will overcome more energy for heat evaporation. All right, so this one is better for cool flame ignition delays. So anyone with higher hydrogen to carbon ratio, will give more specific energy to overcome the heat vaporization. Okay, will release more heat, will produce more heat to overcome the heat vaporization. Okay, then it performs better for cool flame ignition, right? And also, what we want to look at is if you have a higher cyclooctane. I think cyclooctane long time back, for gasoline fuel, diesel fuel, or even jet fuel, they all have cyclooctanes for traditional fuels. Okay, so it will reduce the available hydrogen distribution, which means during the chain initiation, you don't have availability of hydrogen. So you don't have availability of hydrogen, which means it's not easy to grab the hydrogen from you. You don't have the hydrogen availability. I cannot grab hydrogen from you, so you don't have a good hydrogen abstraction. Okay, so that will reduce the reactivity and increase the ignition delay, which means this fuel is not very active. Okay, and we look at the negative temperature coefficient. Like I say, there's a slightly increased for the ignition delay. Okay, for JP5, JA1, and HRJ, they have the specific range for the negative temperature coefficient. So that's the ignition. Okay, and also we look at the soot formation. Okay, soot formation. So this is our setup for counterflow burner, and we use the laser diagnostic. We call laser-induced incandescence technique. Okay, and through our counterflow burner. Okay, and also we use these two equations for calculating the soot volume fraction. Okay, and also we use the thermophoretic sampling. This is we call thermophoretic sampling. What is that? We use the probe. There's a probe, and it's driven by the piston, pneumatic cylinder with piston, and the probe will go through, it will be inserted into the frame, and we'll take the probe with some mesh at the top, and the mesh will catch some soot. Then we catch the mesh, we catch the soot on the mesh, and we go to the TEM, transmission electron microscopy. We go to the TEM and we test the particle size of the soot. Yeah. And also we test, number 3 experiment is we use the small point tester. This is the small point tester. We use this to test the small point. Okay, because the small point has a different chain with the soot volume fraction. You have more soot, you have a shorter small point. You have a longer small point, you have a lower soot. Okay, so we're just trying to validate the trend of the soot volume fraction. So this is our result. This is our result. You can see this is a fuel we produced. Once again, this is the hydroprocess renewable jet. This is a fuel we produced. You can see that in terms of soot volume fraction, it's much lower than the traditional fuel, which means when it burns in a jet engine, you produce much less carbon, much less smoke, okay, compared to the other two fuels, okay. And also we look at a different fuel oxygen mole fraction. The trend is the same, okay. We also look at the small point, okay. You can see our fuel has higher small point, has a highest small point, so it has a lower soot volume fraction, And JP5, which is used in military, compared to the fuel used in commercial aircraft, JA1, they are quite similar. They're quite similar. Okay. Also, we use the TEM, okay, TEM, the microscope, to look at the image of the carbon, image of the soot, okay, burns from the jet fuels. So you can see this is our fuel, this is JA1, and this is JP5, okay. And compared to that, JP5 is higher than, compared to the size, JP5 is larger than JA1, larger than HRJ, okay. Also, we look at the hydrogen content, we call hydrogen to carbon ratio. The higher the hydrogen to carbon ratio, the lower the soot. Okay, so you can see our fuel has 2 point something, the hydrogen to carbon ratio, So it has a lower soot formation compared to these two fuels. Okay, and also when we look at the literature, okay, the soot formation for normal alkanes is less than isomers and cycloalkane, which means you have more isomers, the fuel is more dirty. Okay, you have more cycloalkanes, the fuel emission has more soot, it's more dirty. Okay, also you have more aromatics, the fuel is more dirty as well because it has a higher soot. Okay, because the isomers, it has CH2 CH3 radical, which strengthen the aromatic ring structure. Okay, deriving a C3H3 radical forming the pH, and pH is the precursor of the soot. Okay, so we also test our co-product as well, okay, which we call the hydroprocess renewable diesels. And we can see that soot formation from diesel is also very low, And of course, there's one competitor for this kind of diesel fuels, which is the biodiesel. Biodiesel, the soot formation is also very low. So you can see they are quite similar. What that means is these co-products, we can sell it with at least the same price as the biodiesel. Okay, so we also look at their image, okay, TEM image, okay, and we see for our, this is the image for our diesel fuel, and this is a biodiesel, okay. So in terms of in terms of soot formation, once again, the alkane is lower than cycloalkane, lower than aromatics. So aromatics produce more soot, okay, and then cycloalkane, and then normal alkanes. Okay, so this is the combustion study for our novel fuels, and then we want to look at if we want to commercialize this process, because okay, the combustion test is okay, the production is okay, the combustion test is okay. Then if we want to commercialize this type of fuel, what should we do? Okay, like I said, we need to satisfy at least 3 aspects. Number 1 is energy. Number 2 is economics. Number 3 is environment. Okay, so for this process evaluation, I will introduce our energy and exergy analysis for looking at the energy for the whole process. And also I will introduce they call techno-economic analysis, which means throughout the whole process for producing the new fuels, what is going to be the cost and what is going to be the price if you want to sell it. All right, so this is our process evaluation. We have 3 sources based on number 1 is the source composition, feedstock compositions. Number 2 is the process operating conditions. Number 3 is the laboratory results. Okay, what kind of conversion you have, what kind of selectivity you have. Of course, if you scale up, like you produce little fuels, it's good. But if you produce a large amount of fuel, the result will be different. But yes, it takes some times and period to scale it up to get a pilot plant. It's okay. Okay, but based on the laboratory results, we can produce a process model, okay, through our software, and then we do the mass and energy balances, okay, and then do the cost analysis, okay, and cost analysis is based on the discount cash flow analysis with the capital and operating costs. So we can calculate, okay, what is going to be the amount of money we want to invest to this process, and then if you want to sell your product, what is going to be the reasonable price? Okay, this kind of step, okay, this step is not only used in fuel production; it can be used for everywhere. Okay, if you want to produce, for example, if you want to do the waste to energy process, what is going to be the reasonable waste, the reasonable reasonable price for waste treatment, and what is going to be the reasonable price for your power generation? Okay, so it will work everywhere. Okay, so we base on laboratory operating conditions, equipment quotations, local quotation, and local situation. Okay, and we look at the mass, the energy, and carbon flows. Carbon flow is very important because, like I said, this is good. This is important for environment. And we also look at the energy exergy analysis and compare that we do the pinch analysis. What is going to be the pinch analysis do? The pinch analysis will help us to do the integration. For example, you have some energy, you have some energy loss here, but you have some energy produced too much here. So we can bring out the energy from here and exchange the energy from A side to B side. Okay, that's a good thing for pinch analysis. Number 3 is a techno-economic analysis. We call TEA. Like I say, it will help you to know what is going to be the cost of your process and what is going to be the reasonable price for your product. Okay, so energy, economic, and environment, we call 3E. Okay, so for the mass, energy, and exergy flow, this is our process flow diagram. And we can apply because you can see we have the yellow part is we call exergy flow. Okay, so each of the stream, they have the exergy flow. Okay, and also each of the unit, they have the exergy efficiency. For example, for our process, the hydroprocessing process, the exergy efficiency is 83%. Okay, for cooler, one of the cooler, this is 94%. Cooler 2 is 32%. Okay, one of these two distillation, one of them is 88%, one of them is 93%. Okay, that's their exergy efficiency. So you can define your exergy destruction. So if you go to the thermodynamics chapter 8, the middle of the chapter A, they will tell you what is going to be the energy destruction. So which one has the energy destruction? And then we can combine with the thermal economic analysis. Okay, thermal is, which means per unit of energy, what is going to be the cost? Okay, so we can calculate per unit, per gigajoule of the energy, what is going to be the cost. So for example, for this heater, per unit gigajoule, we have $868.16 of unit energy cost. So this is how we call thermal, which means we combine energy and economics, so thermal economic analysis. Okay, so I can find the cost of energy destruction. So I have the energy destruction, and it costs me how much for fix the energy destruction. Okay, so I can, for the large energy destruction, which means somewhere I lose too much energy. Okay, I can apply the energy integration throughout my pinch analysis. Okay, so I can maximize the process energy efficiency. Okay, so this technique is very important, not only for the fuel production, like I said, but also I can use that for processes, any of the processes, as long as you have the thermal process. You are applying heat, you're trying to heat it up, or you're trying to cool it down. Okay, you apply electricity, so you can apply this model, apply this technology. Okay, and then this is energy part. Economic part, we apply the techno-economic analysis. Okay, this is our process model. Okay, we get a vendor quotation for capital cost. We get a local evaluate operating cost, and throughout the cash flow analysis, we can calculate, and based on some assumptions, we can calculate the reasonable unit price of the product. What is our product? Jet fuel. Okay, this new jet fuel, what is going to be the new reasonable product that will scale? I can have a reasonable scale and make a reasonable profit for this type of products. Okay, so based on our publication in energy, our MJSP, which is minimum jet fuel selling price, the reasonable price, unit price for our jet fuel is $1.43 US dollars per liter. Okay, what is going to be the factors that affecting the prices? Okay, so we call tornado chart. It looks like a tornado. So we make a tornado chart. So the longer, which means you have the higher impact for the price, for the unit price, for the benefit, for the cost. Okay, the shorter, which means you have a less impact for the unit price, for the cost. Okay, we also look at the capacity. You have the bigger capacity, your larger capacity of the plant, the cost will reduce. Okay, the cost will reduce, which means your unit price will reduce. Okay, your unit price, of course, you sell your product and the product is cheaper, then which means your cost is lower, right? So the higher the plant capacity, the lower the cost. But after a certain amount because it will be flat, right? It will be flat. So after a certain amount of capacity, for example, 3,000 tons per day, it will be flat, which means it will no longer affect that much. Okay, and we are using hydrogen for producing fuel. So the higher price of hydrogen, of course, the higher price of the cost, the higher cost, right? And also we look at the operating conditions. When we produce the fuel, we try different temperature, we try different pressure, we try different ratio of, I can call this equivalent ratio, because hydrogen means the if you compare to combustion, hydrogen is the oxygen, oil is the fuel, right? So hydrogen to oil ratio is like equivalent ratio. So compared to the equivalent ratio and compared to the residence time, Okay, different residence time, different temperature, different pressure, different equivalent ratio, you will have different costs. So you will have different reasonable prices. Okay, so this is my conclusion. Back to our, steps. Okay, like I said, for this talk, I only talk for 3 steps. Actually, I only work for these 3 steps as well. The other steps, this is not out of my scope. Okay, so for the first step, the current process is we do the novel fuel development, and in the future we will try to do some decarbonized fuel. For example, we will try to produce hydrogen, or we try to use the CO2 to produce a fuel. That's also the topic for produce novel fuel production. And also for the combustion study, we can also do for our renewable jet fuel. We can try the spray and automation. We can try the flame speed. We can also try the engine operation. These are something we can do in the future. For process evaluations, we model the process. We get a model for process. We do the energy and exergy analysis and economic analysis. There's one more we didn't do, we missed, which is environmental analysis. Okay, so energy, exergy, environment, and economics, we call 4E. Okay, 4E plus R, we call risk. So some people, they are doing 4E process. This 4E plus risk R, so 4E plus R. Okay, also we might want to model some decarbonized process. Okay, so this is my talk, and thank you for listening. And if you have any questions, please let me know. I'll be happy to answer. Thank you.
Thank you very much, Professor Wang.
Thank you.
Okay, I think it's very complete research, starting from create the new fuel for novel jet fuel development, and then going to the testing for in the combustion, and then evaluation combined with the economic calculating. So I think it's very comprehensive research from Professor Wang, and today we have always some knowledge from Professor Wang. And then we're going to the Q&A. So I have 3 section. First section, I open for 3 questioner. So please raise your hand, or you can write in the chat, or in the chat in this room, or you can raise your hand and give directly a question to Professor Wang. So please raise your hand if there is any question for 3 questioner. Okay. Professor Wang, we have participant around the 157, Professor Wang. So I think this is
quite a lot of
very
very good, very successful conference. Yeah.
Okay. So hopefully, I think today is very nice session with Professor Wang. Okay, Hakim Prabowo. Okay, please give a question to Professor Wang.
Excuse me, Mr. Wang. My name is Hakim Prabowo from 11 Maret University. I have one question for you, Mr. Wang. One of our contract in our laboratory is about biomass energy from palm sugar waste, as it's one of renewable energy material. It has good potential for aerospace fuel in the future, Mr. Wang.
What kind of feedstock you're talking about? Can you repeat the?
One of our concern in our laboratory is about biomass energy from palm sugar waste, as is one of renewable energy material. It has a good potential for aerospace fuel in the future, Mr. Wang.
Let me ask you the question is that what is going to be the component? Is that a liquid or
Okay,
solid?
maybe I can help Hakim Prabowo, Professor Bang. This is our student, Professor Bang. So they're my bachelor student. So he tried to give question regarding his research now. So Hakim Prabowo and team is one of student in my laboratory. So now Hakim Prabowo conduct the research in waste to energy. The waste material is from palm sugar material. So is it possible to be the potential or the potential for the fuel for the space or for the aviation fuel for the next generation maybe? So maybe they want to know the potential of his research, Professor Wang.
Okay, thank you for your question. So very important is if this is the solid for agriculture, from agriculture solid, there are two processes you can try. Number one is like Professor Sapoto did from gasification. So you have a gasification, then you have a syngas. Okay, so previously some of the research they are trying to use they call feature choke process. They use some catalyst and they convert this syngas from gasification, and they convert this syngas to some fuels, to some liquid fuels. And the thing is, these liquid fuels are, I can say this liquid fuel is lighter in terms of carbon number, is lighter than the fuel we produced. The carbon range is about C7 to C12 or 13, about this range. Okay, so within this range, okay, they produce fuel. And the thing is, this kind of fuel, in terms of flash point or heating value, is not high enough for aviation fuel. But for blending with aviation fuel, it's good. It's okay. Okay, that's one process. Another process, some people try to use the pyrolysis, thermal pyrolysis, which they use the thermal and decompose your material. And when they decompose your material, it becomes some what we call pyrolytic oil, the liquid. And this liquid, it goes through some process. It depends on the component. Sometimes it doesn't have to. It depends if the component fits the carbon range of the jet fuel and the property fits the specification of the jet fuel, and then okay, you can use that for your aviation fuel. Yes, so two ways you can convert your material to the aviation, for aviation use. Yes, thank you.
Hakim
Thank you,
Prabowo.
Mr. Wang.
Okay. Thank you, Professor Wang. There's any question from the audience for the section 1? We just one questioner. Okay, Professor Wang, I have a question to you.
Yes.
This is very interesting regarding how to reduce the aromatic, and then higher isomer, because this one of the problem in the combustion processes, especially higher salt, and then for the higher isomer is not good for the combustion processes. So how to reduce or to decrease the isomer and then aromatic in your process, Professor Wang?
In my process, actually, there's no aromatics and it's no isomers. Okay, because if you try from glyceride-based oil, what I'm saying glyceride-based oil is palm oil or waste cooking oil. That kind of oil, there's no isomer, there's no aromatics. So isomer comes from isomerization. Aromatics comes from aromatization. So there's no that kind of component. However, if you try to use if you try to start from the oil from pyrolysis, like I said, we call pyrolytic oil. If you try from pyrolytic oil, there's a huge, at least more than 70 or 80% of aromatic cycloalkanes and aromatics. Okay, so how to reduce that? We're working on it. We're working on it now. Yeah. So, like I said, this part is something I need to overcome. Yeah. This is, I can say, this is our weakness. Our weakness. Yeah. So, how to reduce the aromatics from the West-derived pyrolytic oil? That's something we have to try. And now, actually, Achi, the student of you and mine, he's now trying. Now, just right away at this time. Yeah.
Yes, I think this is the problem, and we should overcome this problem of Professor Wang.
Yes. Hopefully, we can work together on this topic. Yeah, something. Yeah, if there's some good information, I'll share with you. Yeah, we both exchange ideas.
Okay, thank you, Professor Wang. There is
Thank
any
you.
question from the participant? Please raise your hand. Okay.
Yeah, one thing I want to make up for the older audience, because you have 150 audience. So one thing I want to say is the process evaluation I just introduced is very helpful, because this kind of process evaluation is okay. For example, for Professor Sapotro, if you have some waste to energy process and you want to make it big, commercialize it, or trying to attract the investors, make attractive to the investors, okay, you need to present to them, number one, economics. Okay, is it money making? What is the profit? That's something they want to know. Number two is it what's going to be the energy consumption? Because energy means the money. So that's why I present a thermoeconomic analysis. Energy means money. So they want to know what's the energy consumption. So you need to have the energy balance for them. Number three, what is going to be the carbon emission? Because everybody's looking at net zero nowadays in the world. Everybody's looking at net zero. So if your process highly carbon emissions, no one will be interested. So what is going to be the carbon emission? Okay, so this 3E, economics, energy, environment, these 3 E's covers all process evaluation. Yes. And somebody get 1R is risk, but it's out of our scope. But 3E is very important for all the processes. All the process. If you want to commercialize your process, this is very important. Okay, thank you.
Okay, Professor Wang. So I think this is okay. There is a question from Ms. Nurul Firdaus by chat, Professor Wang. A few months ago in Indonesia, there were findings from non-academic about the water fuel for motorcycle. This is a training topic in Indonesia, Professor Wang. Water to energy to generate the motorcycle. From research, I understand that converting water to electricity is possible, but not efficient. It's make more energy to convert water into hydrogen and then oxygen. Then it does to produce the energy itself. What is Professor Wang's opinion about this? water to fuel, Professor Bang?
Okay, thank you for your question. Actually, this is the question regarding the fuel cell, which is out of today's topic. But I can provide my opinion is, yes, if you want to get the hydrogen to, produce the hydrogen and go into the fuel cell, it's too slow for, if you want to, you're riding your motorbike pretty fast. This is not very efficient. Okay, we would rather, I always discuss with my students is we call distributed waste to energy equipment. What is distribute waste to energy equipment? I don't know if it works in Indonesia or anywhere in Taiwan, but what I'm saying distributed is like, if you, in Indonesia, if there's electrical motorbike and there's a charging station, right? So if your waste to energy equipment is something like that, you throw out your garbage and it produces hydrogen, and your motorbike goes to that station and charge the hydrogen based on that, that is going to be a big deal. Okay, one thing is you can reduce your waste. Another thing is you produce the hydrogen. And hydrogen will charge your fuel cell, charge your motorbike. Okay, use the hydrogen to produce the electricity. It will be more convenient. The most important thing is you reduce some waste. You reduce some waste. Okay, so that is my opinion. And for your, I don't know if we work in the future, but this is going to be very important thing because it takes time for development. Yes.
Okay, thank you, Professor Bang. Ms. Nurul, there is you want to directly contact with Mr. Wang regarding Mr. Wang's opinion?
Thank you.
Okay, please, Ms. Nurul. Hello, Ms. Nurul, can you hear my voice?
Thank you, Mr. Wang.
Oh, okay. Okay, Mr. Wang. Thank you for your opinion. And then I come again to your suggestion about the 3 point about the economic, energy, and then environment. Yeah. So now in Indonesia also we focusing in the SDGs concern, especially green energy. So many friends and many many researchers in Indonesia give the question how to predict some waste to energy is potential from the technology, from the economic, and then from the environment. How do we calculate, Professor Bang? I think in the last slide, Professor Bang already make the simulation regarding the how to predict the potential energy and renewable energy, and then comparing with the economic perspective.
Actually, one of the things we are trying to concern is these 3E. Okay, these 3E are connected, fully connected. Energy connected to economic, we call thermoeconomic, and also economic is connected to the environment. Okay, it's because now the carbon and every carbon they have the price. Every carbon they have a price. So economic is connected to environment as well. Also, thermal is also connected to the environment. Okay, there's a term, I forget the term, but thermal is connected to environment. Energy is connected to environment as well. Okay, so these 3 topics, they are connecting together. And overall, if you want to choose something that contains energy, economic, and environment, I would say they call sustainability. Okay, sustainability. So if you want to make your process, if you have a waste to energy process, if you want to make your waste to energy process sustainable, number 1, you have to satisfy these 3 these three E: economic, energy, and environment. Okay, and that's the opinion I want to share with you guys. These three processes. Yes.
Okay, Professor Wang. And then maybe another case, Professor Wang. Maybe also the trending topic regarding the bank carbon, and then how to say bank of carbon. So, for example, our research is focusing in the combustion. So combustion, there is one of the pollution source in the world. And then we concern how to reduce the pollution in combustion processes. So what is your opinion regarding the another set green energy, and then environment need the reduce the some pollution emission, and then but in another set all the energy is start from fuel, and then fuel will produce the pollution. What is your opinion, Professor Wang?
Okay. The combustion you're trying to mention is for thermally treating the waste, or to produce the energy for the process. That's something different. Okay. If it's for thermally treating the process, then what you're looking at is, if there's something you cannot deal with downstream. Okay, for example, now at a downstream, after the combustion process, for the downstream, you have, somebody has the waste scrubber, somebody has the trying to stop the NOx, SOx, trying to stop the CO, trying to stop the smoke or soot. Okay, there are many for environmental engineering guy, they do a lot of things for stopping the emission pollutions. So it's quite strong part. But what, like if you do the combustion for the waste treatment, you have to think. I think we have to think about, okay, if we produce something they cannot stop. For example, chlorine. The chlorine, the chlorine and the carbon will produce what? Dioxin. Dioxin is something they cannot stop. So if you try to burn the PVC with the chlorine inside, then chlorine, when they are on the carbon, they'll produce dioxin. And dioxin is very difficult to capture. You can capture the CO, you can capture the CO2, you can reduce the NOx with the ammonia, you can reduce the SOx, okay, with the waste scrubber technology. Many of the pollutions you can stop, but there's something you cannot stop it. That is the chlorine, the dioxin. So that's if you do this. But if your combustion is for providing the energy for the process, then you have to think about, does it worth it? Okay, compared to some other energy sources, for example, the solar panels, wind turbines, or some other sources. Which one is works better for you? And also your heat exchange, something like that. That's it. Thank you.
Okay, thank you, Professor. Okay, there is any question? I open one chance to give the question to Professor Wang. Okay. Okay, I think there is no question, Professor Wang, from the audience, and then the time is maybe in Indonesia now is 2:30, and maybe in Taiwan or 3:34 maybe.
Yes, 3:30.
Okay.
Yes.
So, Professor Wang, thank you very much for your nice insight, nice knowledge for us. I think this is a very valuable knowledge for us, and regarding your research. Maybe let me summary presentation from Professor Wang. Now, Professor Wang conduct focusing in the clean aviation fuel, and he already make some research in order to product the renewable jet fuel, and then Professor Wang already analyzed regarding the potential between jet fuel from GP5, Jet A1, and comparing with the HRG from the Professor Wang. And then one the interesting from the Professor Wang is we should concern energy, economic, and environment. This is very important and have some influence each other. So maybe for the researcher focusing in the combustion, focusing in the environment, and also focusing in the energy, I think this is a valuable statement from the Professor Wang, and we should concern energy, economic, and environment is related to each other. So I think if we want to make the money and get the investor to our research or apply for the research grant, I think the 3 point energy, economic, and then environment is very important to put in our proposal or our research grant. So, Professor Wang, thank you very much for joining in my first international conference. So this is the first international conference. I hope next year the conference will be held by not only by virtual but also by the offline. Offline mean I will invite Professor Wang to come to Indonesia and
thank you very much.
Not a speaker again in next year. And then Professor Wang, the APICS 2022 already prepared certificate for plenary session, especially for Professor Wang. Please prepare the certificate for Professor Wang. Can help me to show the certificate? Okay. Okay.
No, thank you.
This is the certificate for Professor Wang. Thank you very much, Professor Wang. Hopefully, I still waiting your schedule to come to Indonesia, Professor Wang. Hopefully in this year, I will meet Professor Wang and discuss more deeply in order trilogy: energy, economic, and environment.
Sure.
So thank you very much, Professor Wang.
Work more close. We need more close.
Okay, of course, Professor Wang. And
you're too busy. So it's hard to reach you.
Okay, thank you very much. And then the certificate maybe will send by post to Taiwan.
I appreciate it. Thank you.
Thank you very much once again, Professor Wang.
Thank you.
See you in the next section and in the next conference next year.
Okay, thank you.
Bye. And then Tim, return back to the Master of Ceremony.
All right, thank you, Dr. Herman. Ladies and gentlemen, big round of applause for our dear moderator and also our keynote speaker. Thank you. All right, so ladies and gentlemen, right now we're moving on to the closing ceremony, and I believe you all, the participants, you are also waiting for this session as we're going to announce best paper announcement and also another category. So there will be 4 categories. And the first one will be best video presentation award. And then the second category is interactive presenter award. And then we have also best paper award. And last but not least, we have favorite presentation. All right. So I'm going to move on first to the best video presentation award. Okay. And we have 3 winners. I'm going to start from the second runner-up. And the second runner-up goes to... Okay, congratulations. Feeding, yeah, tidak. No, it's different, yeah. Feeding, yeah, okay. Okay, where's the applause, ladies and gentlemen? Okay. And now the second, okay, or the first runner-up goes to Tamara. Okay. And of course, right now we're gonna go to the winner of Best Video Presentation Award goes to Yudo. Can you open your video, Mr. Yudo? Open your video. Come on, we're gonna see. We want to see your face here. Yeah, Mr. Yudo. Okay, where's Mr. Yudo? Come on, open your cam already. Okay, we would like. Okay. Okay, then later we can display your face in the poster. All right, now, ladies and gentlemen, we're gonna move on to the second category, which is Interactive Presenter Award, and we're gonna move on to the second runner-up. All right, the second runner-up goes to Ovid. Okay, Mr. Ovid, I see his name also later in the participant's name. Congratulations. Now we're gonna move on the second, first runner-up goes to Imam. Okay, the name is short, yeah? No, I mean the committee here just gave me the short name and the nickname. And now the winner of Interactive Presenter Award goes to, congratulations to Mutia. Yay! Okay. Okay, now we're gonna move on to Best Paper Award. Okay. For the category Best Paper Award, we only have 1 winner, and it goes to Harry P. Friendly Secret Sharing using integer number representation ID 0213. Once again, ID 0213. Let's give big round of applause, ladies and gentlemen. Where's your spirit? Okay, now we're gonna move on to the last category. Last but not least, this is favorite presentation. Favorite presentation goes to Rudy. Any testimonials maybe from Rudy? Yeah, testimonial from Rudy. Come on, you got the favorite. Come on, testimony, Rudy. Come on, Rudy. Okay, open your cam, Rudy. If you don't open your cam, we will cancel your favorite presentation. Okay? No, he's too shy, yeah? Okay, once again, congratulations, Rudy. Okay, so ladies and gentlemen, dear presenters, with the announcement of the Best Paper announcement, it marks the end of APICS 2022. On behalf of the organizing committee, we would like again to thank you all and also to extend our gratitude for your presence, active participation, and of course, we're waiting for your next participation next year at APICS 2023. I'm Albert Yuana signing out and see you everyone. Good afternoon and have a nice day. Bye.